Hello, welcome back. This is Professor Khan, and we are in week 4 in combustion control circuits, and that is EST 101. This week we will discuss nozzles, combustion chambers, and draft controls. And bear in mind that this lecture was designed to be given over a class of 3 hours, 50 minutes each, so around 150 minutes. So I'm trying to squish all this material into two segments of 15 minutes each. Uh, Having said that, you have to still go over the material, read the book, and attend the Google Hangout to ask some questions to make things a little bit lively, or also ask for questions in the discussion board. Now we are done with the Russell Smith book, and we are in the Nora book, and I will try to give you some information about oil burner controls and some of the tools we use for combustion circuit control. Okay, let's get on with it. So the objectives of this class will identify the oil burner's components for combustions. Probably just saying that will make you think of the flame, right? So we'll talk about the flame, the oil pressure, the air, and the aftermath of the combustion. We will list the characteristics of an oil burner nozzle. How do they differ? How do you replace a nozzle? What does it do? And why is it important to change a nozzle very frequently? We will try to recognize oil burner nozzle replacement types, not one size fits all. They don't all interchange, and I'll try to address the fact that they can be a little bit changeable. We will explain the common problems with oil burners, nozzles, and pumps, some stuff that you'll find and you'll face while you're working in the field. We will also talk about uh, the proper sizing of combustion chamber. And why would you need to know that? Doesn't the designer do that already? We bought a set combustion chamber. Why do we have to worry about that? Well, we'll talk about it more when we get to that slide, but for the time being, you have to know that there's a lot of retrofitting going on. There's a lot of old boilers that used to run on coal or heavy fuel that being converted into regular oil, I mean number two fuel oil or gas. So it's good to have an idea that what size of flame do you need in that combustion chamber. Okay, explain how to properly size a chimney and venting system for an oil burner, and that has a lot to do with the code. And I'm counting on you will to have this expertise and to know where to look when you need to find this information. I know I'm throwing a lot of information on you, but I think it's good to uh, have it come across your head and you know where to look if you need to find that. Okay, combustion. We did talk about the basics of combustion. We always need the correct mix of fuel, and we said, I hope I have the equation here, maybe I don't, but we know that we mix fuel, which is hydrocarbon, with air, and basically we are using the oxygen, and we need a spark, and we will get heat and carbon dioxide, sometimes carbon monoxide, water, and sometimes also some SOx and NOx, which are SOx and NOx, nitrogen oxide, and sulfur oxide. So we need the correct amount of fuel because we need to burn the fuel completely. We don't want any unburned fuel, and you don't want to have excess gas as well. Any the right amount of air is very important. So keep that in mind, and usually you adjust the air last, and it's the final touch when it comes to complete and correct combustion. If any of you ever had a car, an old car from the 80s or early 90s, probably had to deal with carburetors and adjusting the air for that carburetor to have the right combustion. Nowadays, you don't have to deal with that. Everything has been automized. Okay, what is atomizing? So for us to burn the oil properly, the oil has to be atomized. The word atomize means kind of something small like an atom. It's making actually changing the oil into vapor by pushing it through a small orifice. It's like a spray. So That's a fancy way of saying like spraying the oil, but it's not, it's more sophisticated than spray. If you look at the oil, it's more of a mist. It's very small droplets. Okay. Clean combustion then is burning the entire fuel. No excess fuel, no smoke whatsoever. Okay. Moving on. What is the ignition point of fuel oil? I've seen different references, and I think it depends on the type of fuel, but I've seen something from 500 all the way to 637, 630, 600. It depends, I guess. I don't know which source to go with, but I'm gonna go with the NORA book and say it's around 637 degrees Fahrenheit. That's the ignition fuel. The ignition point. The ignition point is the temperature where the fuel will start to combust and continue to burn. Uh, I also would like to define confined space. That is a question that's going to happen, that's going to take place in the oil burn technician exam, and also you'll face that in some of the in the midterm. I'm going to ask you this question, and also in one of the homeworks. So, what is confined space? Let's think about it a little bit. Confined space is 50 cubic feet per thousand BTU hour. So, if and this BTU hour pertain this is pertaining the boiler. So there's no boiler at 1000 BTU. Most boilers, let's say 30,000 BTU. So for every 1000 BTU of that boiler, there should be 50 cubic feet. Any less than that, and that location where the boiler is located is considered confined space. So for 30,000 BTUs, you're going to multiply 30 by 50, so that's going to be 3 times 5, 150, and it's going to be 1500 cubic feet, if I did that correctly. That's supposed to be the space where the boiler is located. If it's less than that, then it is considered a confined space, and it has to be ventilated before you do any work in that. And it does happen. It is possible you see a small little basement with the boiler in it, so you're not allowed to enter that place if there is no proper ventilation. You have to go and review the confined space regulation. It has to be off, first of all. It has to be ventilated. And sometimes, if there is no possible way, you might need a breathing apparatus to go with you. And that's the code, and that's for your health. So just bear in mind of what's happening about confined space and how do you calculate confined space. If you have any questions, please let me know. Okay, moving on. Where's my cursor? Okay, I got it. Uh, we talked about atomizing, and this here is a photo of the nozzle. So this is my nozzle being disconnected from the nozzle uh, assembly, and in here you see how the fuel is concentrated here in the little dots. This is the small droplets and the spray that coming out of the nozzle. And again, as we get closer to the nozzle, it's more concentrated, and you see the fuel is being pushed through the strainer over here and all the way through the smaller orifice. And there's a lot of research and engineering that goes into putting together a well properly assembled nozzle. So it's a good idea to uh, not change the geometry of the nozzle, and also not to drop it. You see this little space is very tight, so if you drop a nozzle, probably you have to change it. And you can see how with the overheating will ruin the nozzle, and also the orifice size change will also uh, cause the nozzle to malfunction. So three major influences on a nozzle pattern. The three major influences on nozzle pattern. By the pattern, we mean the spray of the nozzle. How does it look? Is it like oval? Is it sprayed? Is it big angle, small angle? It's the flow rate, and the flow rate is determined by uh, Oh, I keep doing this. Do it again. Try. Okay, flow is determined by the pump. It's the GPH, gallon per hour. So it's always a volume per time. The viscosity of the fuel and the pressure. So the flow rate and the pressure is dictated by the pump. The flow rate is also dictated by the pump and by the size of the orifice on the nozzle. And the viscosity is a function of the temperature and also the pressure. So Probably if you remember from the Energy System Lab 1, when we increased the pressure, we did change the flame shape and size. So hopefully that gave you an idea of how the pressure contribute to the nozzle pattern and burning of the fuel. As you see here, this is the spray angle, how big and small it gets, and it's basically called a throw, and some of them are more suitable for different shape chamber. I mean, check this one out. It's very small, so you need from 70 to 90, and smaller angle from 30 to 70 will give you longer throw. So you want the flame to be inside the chamber and engulfed and not hitting any of the walls. So if you see if the flame is fading on these corners and going in the middle of the chamber. For replacing the nozzle, you always want the exact replacement, especially when it comes to the spray angle and the flow rate. Those two information are engraved on the nozzle. Also, try to get the same brand. Actually, you should get the same brand unless it's been discontinued, and you have to find if it's discontinued, you might be able to match the same flow rate and pattern on the uh, nozzle. Brand is not interchangeable, but if you have to, you might try to get the closest thing to it, and you might have to do some adjustment as well into the pump pressure. Never alter or change the nozzle with a different type unless you did the proper calculation for the chamber and you know it's necessary. This might cause a problem. It might overheat one spot in the chamber more than the other and can cause the boiler to fail. Uh, having said that, if you were to change the chamber, make sure you know what you're doing and you did the proper calculation and you get some approval. Otherwise, you'll be liable for that boiler failing, especially if it's a new boiler. With old boilers, you can do the sizing and hope for the best, and probably the warranty on that boiler has already been gone. Do not touch the strainer or the orifice. Try to minimize touching the nozzle. Use a clean rag to put it in place. And if you drop it again, sorry to say, if you drop it, you have to change it because that will change the geometry of the nozzle. Use clean hands. You might be working with oil with some grease. If you again put any kind of stains on the nozzle, it's not going to function. If you look at it, it's very, very fine details in the mesh. You might have a small grain of sand or dust goes into the spray angle that will change the way it spray. And if it sprays incorrectly, it will cause you to drop some oil in the chamber. And that's a problem because you'll have a lot of smoke. And again, we said in the beginning of the class that we are striving for complete combustion. Avoid sand dust or any other objects to touch the nozzle. Of course, if you drop it, it might scratch, and again, it will change the passage of oil that goes through it. Never disassemble, try to change the strainer or clean it. That's a bad practice. Use clean tools, avoid scratching, and they last for up to 2 seasons. I personally prefer to change them every season whenever possible uh, because they do have a big influence on the spray and the efficiency of the flow inside the boiler oil furnace. More information. They should not be very hot. If you turn it on and take out the assembly and it's very hot, you know something is wrong with the location of that ignition assembly. They could be the reason for a smoky fire. Again, never disassemble. That's another tip. We said that already. So this is a repetition. Okay. Other problems. After drip. What is after drip? That's when you turn off the boiler and it's still having oil, small droplets coming into the chamber. It could be a problem with the pump and the shutoff valve. They could be leaking a little bit. It could be air in the nozzle line. So you might want to purge the line and make sure there's no air bubbles in there. Or it could be excessive heat coming from the chamber. It's not well insulated or something of that sort. So if you have a defective shutoff valve or a pump, the way you find out about that issue is if you uh, perform a pressure test and a vacuum test on the pump, and I did show you how to do that in the first Energy System Lab. So you install the pressure, you set the pressure, you turn off the pump, and the pressure should drop to 20% and stay in there. If it keeps dropping, it means something is wrong with that pump, and you might first want to bleed the pump, make sure all the connections are tight, and try it again. This is what causes the after drip. You have small droplets of air inside the nozzle line. When you turn it off, the pressure has been decreased, so these things will expand and will push some fuel outside the nozzle, and they will accumulate in the floor of the chamber. When you turn on the fire again, it will cause you to have some smoke. So chamber and chamber sizing, they are very connected to each other because uh, the chamber has a set size, and the nozzle and the fuel and the shape of the flame is designed for that exact chamber. They are sized based on the gallon per hour firing rate. So that tells you that there's a relationship between the nozzle and the chamber. The requirement is done by square inch for combustion in the chamber. And there's a chart here that shows you what is the oil consumption that should be thrown into the chamber based on the square area of the chamber and the volume. And this is the dimension in case it's a square, in case it's long, or in case it fits round. So this chart kind of give you a general rule on how do you size a chamber. And why are we doing this? This is in case of conversion. You want to convert charcoal to oil. You need to change the burner on an old boiler. You use that chart to help you understand how much oil should be pumped inside that chamber. Again, more about the dimensions and the location and where do you center the burner inside the boiler. So this is the locations of the center of the burner, and based on the size of the chamber. And you want, again, if you notice, you don't want the flame to be hitting the floor or the top heat exchanger or the sides. And if it does and you did not pay attention to it, this can cause one of those areas to overheat, and eventually the boiler will crack. And again, we're going all the way from 0.5, which is the minimum firing rate, all the way to 2.75. And these are the dimensions: length, width, and the center, which is the center of the burner to the floor of that chamber. This is very good information, and I hope you download the PDF and keep that bookmarked for future reference. Okay, I'll pause right now and I'll do the other video for part 2.